Okay, example 7 is an all-inclusive example. It deals with everything we did in chapter 4.1, 4.3, and now 4.4. All right. Find the horizontal asymptotes of the curve. That is the 4.4 contribution. A horizontal asymptote happens as x approaches positive or negative infinity. What happens to the graph? All right. So, if I do the limit as x approaches infinity of 2x over x squared plus 1, and the limit as x approaches negative infinity of 2x over x squared plus 1, that's going to get me the horizontal asymptote or asymptotes if there are any. So again, anytime they ask for horizontal asymptotes, that's your technique. Do the limit as x approaches both positive and negative infinity. Usually they're the same answer, sometimes they're different. But usually the same. These are both just polynomial rational functions, so multiplying by 1 over the highest power of x. Highest power of x in each case is x squared, right? Mm-hmm. So times 1 over x squared on top, 1 over x squared on the bottom. That leaves me with limit as x approaches infinity. On top, 2 over x. On the bottom, 1 plus 1 over x squared. And this will be the same result, right? Limit as x approaches negative infinity of 2 over x over 1 plus 1 over x squared. With polynomial pieces, the only difference between positive and negative infinity is the sign of 0. You're either getting a positive 0 or a negative 0. Okay. And I know that might sound weird because 0 doesn't have a sign. But think of positive 0 as 0 coming from the top, negative 0, 0 coming from the bottom. Okay. They'll both equal 0, but which direction are they coming from? As x approaches infinity, we'll try this again. We asked the last question, nobody knew until a little while. 2 divided by infinity equals what?
0.
0. Excellent. All right. And 1 equals? 1. And 1 over infinity squared equals? 0. So 0 over 1 plus 0 is equal to 0, right? Mm-hmm. And that's a positive 0. That's a positive 0 because 0 squared is a positive, obviously, right? And again, positive 0 over 1 is 0. On the bottom, same deal. What's 2 over negative infinity?
0.
Negative 0. If you want to get really technical about it, still 0. You guys weren't wrong with 0, so I'm just picking on you a little bit here. What does 1 equal?
1.
1. And 1 over x squared?
Plus 0.
Is positive 0. Very good. Because negative infinity squared is positive infinity, right? Infinity squared. So 1 over positive makes positive 0. So both of those come out to 0. So y equals 0 is the horizontal asymptote. And again, if they ask you to find horizontal asymptotes, that's how you do it. Set the limit as x approaches infinity for the function, and then work it out. Let's make this green. Make my asymptotes to be green. So y equals 0. Horizontal asymptotes are always a horizontal equation. It's also squinting. Horizontal equation. Horizontal equation is always y equals number, and the number is going to be whatever the limit equals. The limit equals 0, so that's what y equals. That's how you find a horizontal asymptote every single time. As far as graphing horizontal asymptotes is concerned, we simply graph a dashed green line. Green because I chose green for the color. Y equals 0 is the x-axis. So all I know for this graph at this point, as I go towards positive infinity, go as far as I can this way, and go as far as I can that way, I'm getting closer and closer to 0. Now, I kind of was playing around with this a little bit, but I was getting into positive and negative zeros. This is a positive 0, right? That also gives me the knowledge that as it comes towards infinity on this side, it's going to be coming from the top. This is a negative 0. As it goes towards infinity, it's coming from the bottom. Okay, so again, I was being a little playful there with it, but positive 0 and negative 0 gives me a lot of insight into which direction I'm coming from also. That's helpful a little bit. I don't have to put the lines on my graph yet, but just know that that plus and minus 0, that's the purpose of it. If you really focus on the signs of what the zeros would be, that establishes where you'd be on the graph. All right. Everybody got what they need off of this now? So I can string it up and get some room to work. More squinting. Put it up there. That's a good place for it. Okay, moving on. Intervals of increase and decrease, concavity, that's first and second derivative stuff, right? So, I can say I got a rational function if I do y prime, and again, this would be a scratch sheet of paper thing to do, so let's get a scratch sheet of paper here. And if I have y equals 2x over x squared plus 1, and I find the first and second derivative of this thing. So it's a quotient, so I use the quotient rule, y prime equals low d high, x squared plus 1 times 2, minus high d low, minus 2x times 2x, over the square of what's below, that's x squared plus 1, the quantity squared. And I go on to simplify that as much as I possibly can. 2x squared minus 4x squared is negative 2x squared. 2 times 1 is plus 2 over x squared plus 1 squared. So y prime is done. Y double prime, once again it's a quotient, so I use the quotient rule, low d high minus high d low. When I do d low is going to be a quotient, it's going to be a chain rule, right? Because we got an object to a power. So, if I do low d high first, that's going to be x squared plus 1 squared. D high is just negative 4x. Minus high minus negative 2x squared plus 2. D low, bad planning on my part, let's put it here. If I do d low, here's low, right? Let me circle in red. This is low. 2 times x squared plus 1 to the first times 2x. Just a basic chain rule going on there. It's a power structure, so it's a power rule. 2 times base to 1 lesser power, but then derivative of base 2x needs to be multiplied by it. A lot of you are forgetting this little piece here. So be careful of that. Over the square of what's below, that's just going to be x squared plus 1 to the fourth. Now, rational functions, that's polynomial stuff over polynomial stuff. Rational functions. This happens almost every single, in fact, I'm going to say it happens every time. I'm going to go out on that limb and say, yeah, it happens every time. All right? Whatever power this is double that power. The second derivative should be 1 power more than that. So first power, 1 power more than that's the second power, 1 power more than that's the third power, but look, it isn't the third power. That's not a coincidence, that happens all the time on these problems. If you look at the object that we have here, this product is a term. This product is a second term, and this is a third term. There's 3 terms created by the quotient rule. Low d high is term 1, minus high d low is term 2, over the square of what's below, that's term 3. Always 3 terms. Look at the 3 terms and notice that they can all contain x squared plus 1 to a power, right? The lowest power they share is the first power. There's a first power in this one, a first and another first power here, and a first and a third here, right? The first power in each of those cancels. So x squared plus 1 to the first comes out of that, leaves me with x squared plus 1 to the first. X squared plus 1 to the first gets out of this, leaving me with nothing. 1 officially. And on the bottom, x squared plus 1 to the first comes out of that, leaving me with x squared plus 1 cubed. That will happen every time you get a rational function. If you do not do that, you just cost yourself an extra 15 minutes to try and figure out all the stuff necessary to do that. You cost me an extra 18 minutes to probably try and grade your paper because I got to rework the problem because there's no reason in the world I'd ever do that. But some of you guys like to do that. So let's take something and just make it more difficult than it has to be. That always happens. Expect it, look for it, prepare for it, and plan for it. So you get the simplest stuff possible. The other place I've seen mistakes happening quite often, there's no parentheses around this term. The high is a parenthesis, a binomial parentheses around it. So what's happening up here? Negative 4x times x squared plus 1, the black part, is going to be negative 4x cubed minus 4x. The red part, or sorry, green part, I got minus this times this times this. This is a monomial, 2 times 2x times a binomial. So this 4x that's happening here is actually negative distributing through there, right? So negative 4x times negative 2x squared is positive 8x cubed. Negative 4x times positive 2 is negative 8x. over the square of what's below, just keep it x squared plus 1 cubed. From here to here is calculus, quotient rule. Canceling all these x squared plus 1s is algebra. Distributed property, algebra. A lot of your mistakes are happening in algebra. And again, it just comes down to how much practice have you been putting into those problems. So be careful with your algebra. So last step, combine like terms. 8x cubed minus 4x cubed is 4x cubed. Negative 4x minus 8x is negative 12x, all over x squared plus 1 cubed. So I got a first derivative here, a second derivative here, right? So we're good to go. Everything we need for our stuff is right there. Let me go 2 pages again. Write those down. So y prime is equal to negative 2x squared plus 2 over x squared plus 1 squared. And y double prime is equal to positive 4x cubed minus 12x over x squared plus 1 cubed. All right. So if we move on to intervals of increase and decrease, we need critical numbers. Critical numbers from the first derivative. So increase, decrease, tell me when the graph goes up, when it goes down. If it changes from up to down at a real value, it's maximum. If it goes down to up, it's hitting a minimum value, right? So if I take the first derivative here, find critical numbers, we have 3 criteria for critical numbers. Criteria 1 is the derivative equals 0. We've seen rational functions now recently for the last 3 weeks, right? When you see a rational function, criteria 1 happens when the top equals 0. A fraction equals 0 when you have 0 divided by number. When the top equals 0, criteria 1 happens. Criteria 2, polynomial does not exist, occurs when the denominator equals 0. So whenever you look at a rational function, the top equals 0 answers question 1, the bottom equals 0 answers question 2. Every time. Okay? So when does negative 2x squared plus 2 equal 0? Negative 2x squared plus 2 equals 0. So that means that 2 is equal to 2x squared, right? That means x squared is equal to 1, right? That means x equals?
Plus or minus.
Plus or minus 1. Very good. So again, it equals 0 when the top equals 0. Top equals 0 plus or minus 1. When does x squared plus 1 equal 0?
X equals 1.
Let me just, right here, I'm going to graph x squared plus 1. 0, 1, 1, 2, negative 1, 2, 2, 5, negative 2, 5. When does that equal 0? Doesn't. Never. That's what equals 0 looks like across the x-axis. That one doesn't, right? Okay. X squared plus any number never equals 0. Y equals x squared starts at 0, 0. If you add anything, it just raises it up off the x-axis and you touch the x-axis. So it never equals 0. So x squared plus 1 squared will never equal 0. What are the endpoints? There aren't any. So the only critical numbers of the first derivative are plus and minus 1. So negative infinity to negative 1, negative 1 to 1, and 1 to infinity are going to give me all the necessary information I need to find increasing, decreasing. I want to pick test points on those intervals, so I'm going to pick negative 2, 0, and 2. And all I got to do is evaluate the derivative at those numbers. And even better than that, I only have to evaluate the top of those numbers because the bottom is always positive, right? If I just know what the top equals, that's good enough. So, negative 2 squared is 4, times negative 2 is negative 8, minus 2 is negative 6. 0 plus 2 is positive 2. 2 squared 4 times negative 2 is negative 8, plus 2 is negative 6. Negative, positive, negative, it decreases, then it increases, then it decreases. The critical numbers both came from criteria 1, which means they're actual real numbers that actually work always, right? There's no asymptotes there. That means that decrease to increase hits a minimum, and increase to decrease hits a maximum. So just like that, I've got some specific values of x that are important for me. If I want to make an xy chart at this point, I can do that. We'll do that in a minute. All right, that's everything I need from the first derivative. I've got my decreasing, increasing intervals. I've got my min and max. Everything I need to know is there. Second derivative, criterion 1. When does the top equal 0? 4x cubed minus 12x equals 0. How do we solve that?
Take a 4x out.
Very good. Take the 4x common factor out. That leaves me x squared minus 3 equals 0. Then what do we do?
Well, 4x equals 0.
4x equals 0. Or x squared minus 3 equals 0, right? So this gets me x equals 0. This gets me x squared equals 3. So x equals plus or minus the square root of 3. About 1.73 if you wish to evaluate it on a calculator, which as far as calculus is concerned, if we're trying to graph things, decimals are perfectly fine with me. If I'm trying to build a bridge, I'll probably keep the square root of 3. If I'm trying to graph a function, 1.73 is perfectly fine. So we get 3 critical numbers in the second derivative, so we're going to go from negative infinity to the smallest one, from that one to the next one, from that one to the next one, and from that one to infinity. I just skipped a step, I just realized. What did I skip?
2 and 3.
2 and 3, all right, so 1, x equals plus or minus 0, 1.73 and 0. All right, criteria 2 and 3. Okay, when does the bottom equal 0?
Never.
Never, because x squared plus 1 still never equals 0. What are the endpoints?
There's no.
There aren't. Never. So good. All right. Just getting a little ahead of myself again. Just always verify that those criteria are all met. Critical numbers meet all 3 of those criteria. If they don't, then you skip it. They're not moved together. All right. And again, the bottom is always positive. We just have to check the top. I'm going to pick -2, -1, 1, and 2 as my test points. All those test points lie within the intervals. I'm simply checking to see if the top is positive or negative with those numbers. If I put -2 in place of x, I'm going to get -8 times 4 is -32, plus 24 is negative something, right? -8 maybe? All right, if I put -1 in, I'm going to get -4 plus 12 is +8. If I put +1 in, I'm going to get 4 minus 12 is -8. If I put 2 in, I'm going to get 8 times 4 is 32, minus 24 is +8. So it's concave down, concave up, concave down, concave up. And it's going to have an inflection point, inflection point, inflection point at those 3 numbers. So just like that, I found 5 critical numbers altogether. That gave me 5 values of x that are very important, right? So if I want to do an xy chart at this point, I'm going to put 1 and -1, 0, 1.73, and -1.73. All 5 of those points, those values of x are going to be useful because they have some importance. 1 is a maximum, -1 is a minimum. All 3 of these are inflection points. Our graph that we're trying to graph here is 2x over x squared plus 1. So I go with my calculator, y equals, clear all that stuff out, 2x divided by parentheses, x squared plus 1, and parentheses. Some of you are getting a little bit sloppy with the parentheses, just not using them when you need them. Anytime you divide stuff that's more than one thing, you got to use parentheses. Go to our graph, our table, and again, I'm just going to substitute these 5 numbers that we found. My 5 critical numbers: 1, -1, 0, 1.73, and -1.73. So 1, 1, -1, -1, 0, 0, 0.8665, so 0.87, and -0.87. Okay. So imagine that we have all this stuff. We have this asymptote at 0, right? A maximum of 1, a minimum of -1. Seems like everything's going to stay within that -1 to 1 region, right? As far as I can tell. So maybe I'm going to scale the y-axis as a 0.25 scale. Let's go x at a 0.5 scale because we only went to 1.73. All right. So, 1, 1, 2, 3, 4, 1. So 0.51, 0.25, 0.5, 0.751. Negative 0.5, negative 1, 0.25, 0.5, 0.751. 0, 0, simple. 1.73, 0.5, 0.1, 1.5, 1, 2, so 1.73 would be here. 0.87, 0.25, 0.5, 0.75, 0.87 would be about here. And negative 1.73, 0.75, 0.87 would be about here. All right. Now, for me personally, if I'm graphing things, this is an inflection point, this is a minimum, this is an inflection point, we have a maximum and an inflection point. All right. For me, I graph inflection point to inflection point. All right. It's concave down from negative infinity to the inflection point, so the graph's going to be going like so to that point. Notice I'm leveling it off at the asymptote. From inflection point to inflection point here, it's concave up. So there, it's concave up through the minimum. Then it's going to be concave down to the next inflection point through the maximum. Then it's concave up to infinity, like so. So to me, that's what the graph should look like. Again, it's concave down to the first inflection point, concave up to the next inflection point, passing through the minimum value. Notice I didn't go way down here because the minimum's right there. So again, concave up and bottoming out at minimum. Concave down, maxing out at the maximum, and then concave up for the rest of it. So I just go from inflection point to inflection point, let the concavity hit. If there's a maximum or minimum, make sure that I bottom out or top out those numbers. And there's the graph. If you want to verify that graph, let's see, 1, 2, 3, negative 3 to 3. Let's go negative 1.5 to 1.5. Hopefully it looks about the same. All right, so that's all there is to it. If it asks you to sketch the graph, please sketch the graph. Use all the stuff you've learned in all 3 chapters in order to do it.